As we have learnt earlier, a constant current-carrying conductor produces a magnetic field around it, and a change in the magnetic field with time induces an electric current in a closed conducting loop. Maxwell showed that a change in the electric current or the electric field with respect to time produces a magnetic field. To calculate the magnetic field produced by the change in the electric current with respect to time using Ampere's law, consider the process of charging a capacitor C by connecting it to a time-dependent current IT. As a first case, consider an imaginary circular loop S1 of radius r, which is outside the capacitor. The plane of the circular loop is perpendicular to the direction of the current in the conductor, and the center of the circular loop coincides with the conductor. The magnetic field due to the current in the conductor at any point on the circular loop is along the circumference of the circular loop. The magnitude of the magnetic field at any point on the circular loop can be calculated by using Ampere's circuital law. Consider a small element, dl, at a point P on the circumference of the circle. Let B be the magnetic induction at the point P. From Ampere's circuital law, integral over the closed loop B dot dl is equal to mu naught IT. Since B dot dl is equal to B dl cos theta, Ampere's law can be written as integral over the closed loop B dl cos theta is equal to mu naught IT, where theta is the angle between the directions of the magnetic field B and the small element dl along the circumference. Since the direction of magnetic field is along the circumference of the circular loop, angle between the magnetic field and the length of the element dl on the circular loop at that point is 0 degrees. Cos 0 is equal to 1. Then, integral over the closed loop B dl is equal to mu naught IT. Let this be equation 1. The circular loop is symmetric with respect to the conducting wire. Hence, the magnitude of the magnetic field is constant at any point on the circumference of the circular loop. That is, B into integral over the closed loop dl is equal to mu naught IT. Here, integral over the closed loop dl is the total length of the circular loop. That is, the circumference of the circular loop. Thus, integral over the closed loop dl is equal to 2 pi r. Let this be equation 2. Substituting the equation 2 in the above expression, we get B into 2 pi r is equal to mu naught IT. Hence, the magnetic induction B is equal to mu naught IT by 2 pi r. Let this be equation 3. Using the equation 3, we can calculate the magnitude of the magnetic induction at any point on the circumference of the circular loop S1. Now, as a second case, consider another surface to calculate the magnitude of the magnetic field at the same point P using Ampere's law. Consider a surface S2 in the shape of a cup such that the bottom surface of the cup lies between the plates of the capacitor and the open surface of the cup coincides with the circular loop taken in the first case. Let the point P be on the open surface of the cup. The surface S2 which is in the shape of a cup, does not touch the conducting wire and the plates of the capacitor. Thus, the current passing through the surface S2 is equal to 0. From Ampere's circuital law, integral over the closed loop B dot dl is equal to mu naught IT. Since the current enclosed by the surface S2 is 0, integral over the closed loop B dot dl is equal to 0. Hence, the magnitude of the magnetic field at point P on the surface S2 is equal to 0. Thus, Ampere's circuital law gives two different results at the same point P. In the first case, the magnetic induction at point P, B is equal to mu naught into IT by 2 pi r. In the second case, the magnetic induction is 0 at the same point, which is a contradiction. This contradiction arises with the use of Ampere's law, which must be missing some term. Then Maxwell suggested that on close observation of the surface S2 between the plates of the capacitor, we can write the missing term in terms of the electric field that passes through the surface S2. This electric field produces some current between the plates of the capacitor. Now, let us calculate the current due to the electric field between the plates of the capacitor. Let A be the area of cross-section of the plates in the parallel plate capacitor. Q be the charge on the plates of the capacitor, and sigma be the surface charge density. Then, sigma is equal to Q by A. Let this be equation 4. We know that the electric field between the plates of the capacitor E is equal to sigma by epsilon naught, where epsilon naught is the permittivity of free space. On substituting the equation 4, we get E is equal to Q by A by epsilon naught, which is equal to Q by A epsilon naught. Let this be equation 5. Here, the electric field is perpendicular to the plane of the bottom surface of S2. Hence, the area vector of the bottom surface of S2 and the electric field are in the same direction and maximum electric flux passes through the surface. We know that from Gauss's law, the electric flux through the surface phi E is equal to EA. Here, A is the area of the surface through which the electric field passes, that is, equal to the area of the plates of the capacitor. On substituting the equation 5 in Gauss's law, we get the electric flux phi E is equal to Q by A epsilon naught into A. That is, the electric flux through the surface S2 is equal to Q by epsilon naught. Let this be equation 6. Equation 6 can be rewritten to get the charge on the plates of the capacitor, that is, Q is equal to phi E into epsilon naught. Due to the time-dependent current source, the charge on the plates of the capacitor changes with time. Thus, the current due to the rate of change in the charge I is equal to dQ by dt. On substituting the charge, we get the current I is equal to d phi E into epsilon naught by dt, which can be written as I is equal to epsilon naught into d phi E by dt. Let this be equation 7. This is the missing term in the Ampere's law, which is the current due to the changing electric field between the plates of the capacitor. This current is called displacement current, denoted as ID. Hence, Maxwell's generalization of the Ampere's law is that the sources of magnetic field are both the current in the conductor due to the flow of charges called conduction current denoted by IC, and the displacement current due to the changing electric field between the plates of the capacitor. Thus, the total current enclosed by the surface S2 is the sum of the condition current and displacement current, that is, I is equal to IC plus ID, which is equal to IC plus epsilon naught into d phi E by dt. Now, the Ampere's law can be written as integral over the closed loop B dot dl is equal to mu naught into IC plus ID, that is, integral over the closed loop B dot dl is equal to mu naught IC plus mu naught epsilon naught into d phi E by dt. This is known as the Ampere-Maxwell law. Let this be equation 8. In explicit terms, when the point P is considered outside the capacitor, the source of the magnetic field at that point is only the conducting current. Since outside the capacitor plates the displacement current ID is 0. Thus, integral over the closed loop B dot dl is equal to mu naught into IC. If we consider the point P inside the capacitor plates, the source of the magnetic field at that point is only the displacement current. Since the conduction current between the capacitor plates is 0. That is, integral over the closed loop B dot dl is equal to mu naught into ID. Even though there is no conduction current at the point P inside the capacitor, there is a magnetic field due to the displacement current, which is due to the time-dependent electric fields. Hence, the change in electric field with time can produce a magnetic field, and the change in magnetic field with time induces an electric field. This symmetry explains the existence of electromagnetic waves, which you will learn in another module. Now, let us have a look at the set of equations originated from different sources that helped the study of electromagnetic waves. These equations are popularly known as Maxwell's equations. They are integral over the closed surface E dot dA is equal to Q by epsilon naught. Integral over the closed surface B dot dA is equal to 0. Integral over the closed loop E dot dl is equal to minus d phi B by dt. And integral over the closed loop B dot dl is equal to mu naught IC plus mu naught epsilon naught into d phi E by dt. In earlier lessons, we have learned that charges at rest produce an electrostatic field, and charges in a steady current carrying conductor produce a constant magnetic field around it. But Maxwell explained that accelerating charges produce both an electric field and a magnetic field that varies with respect to time. And these fields propagate in the form of a wave called the electromagnetic wave. To explain the production of an electromagnetic wave, let us consider an oscillating charge, which refers to an accelerating charge, oscillating along the y-axis with some constant frequency. The oscillating charge produces an oscillating electric field along the direction of the oscillations of the charge and propagates along the x-axis. Here, the frequency of the electric field is equal to the frequency of the oscillating charge. We know that an electric field changing with respect to time produces a magnetic field. The oscillating electric field produces a magnetic field which oscillates perpendicular to the direction of the oscillations of the electric field, that is, along the z-axis, and propagates along the direction of the x-axis. Now, the oscillating magnetic field produces an electric field which is oscillating perpendicular to the direction of the oscillations of the magnetic field and propagates along the x-axis. Thus, the oscillating electric field and the oscillating magnetic field regenerate each other and propagate along the x-axis. This wave is called an electromagnetic wave. Its frequency is equal to the frequency of the oscillating charge. According to the law of conservation of energy, the energy lost by the oscillating charge converts into the energy of the propagating wave. We know that visible light is an electromagnetic wave with frequency in the order of 10 power 14 Hz. Is it possible to produce visible light with an AC circuit in which the current oscillates with a frequency equal to that of visible light? The maximum frequency that can be produced with modern electronic circuits is in the order of 10 power 11 Hz, whereas the frequency of visible light is in the order of 10 power 14 Hz. Hence, visible light cannot be produced in an AC circuit with oscillating currents. From the above discussion about electromagnetic waves, it is clear that the electric field E and the magnetic field B oscillate perpendicular to each other and perpendicular to the direction of propagation of the wave. Now, let us discuss the mathematical analysis of the electromagnetic wave. As the wave propagates in the direction of x-axis, the electric and magnetic fields oscillate along the y-axis and z-axis respectively. These fields vary sinusoidal along the x-axis with respect to time. The electric field and the magnetic field can be written as Ey is equal to E naught sine kx minus omega t and Bz is equal to B naught sine kx minus omega t respectively. Let these be equations 1 and 2 respectively. Here, E naught is the maximum value or amplitude of the electric field. B naught is the maximum value of amplitude of the magnetic field. And K is the wave number related to the wavelength of the wave lambda. That is, K is equal to 2 pi by lambda. Let this be equation 3. Omega is the angular frequency. It is related to the frequency of the wave by the equation omega is equal to 2 pi nu. Let this be equation 4. On substituting equations 1 and 2 in Maxwell's equations for electric field and magnetic field, we get a relation between omega and K as omega is equal to Kc. Let this be equation 5. Here, c is the velocity of electromagnetic wave that is equal to 1 by square root of mu naught epsilon naught. On substituting the equations 3 and 4 in the equation 5, we get c is equal to nu lambda. From Maxwell's equations, we also get the relation between the maximum values of the electric field and the magnetic field as E naught by B naught is equal to C. That is, the ratio of maximum value of the electric field to maximum value of the magnetic field of an electromagnetic wave is equal to its velocity. We have learnt about the different types of waves. Sound waves in air are longitudinal waves that propagate in the form of compressions and rarefactions. Water waves on the surface of water are transverse waves. It propagates in the form of crests and troughs. This shows that waves propagate through a material medium. In the early 1800s, scientists believed that there must be a material medium spread throughout the space in which an electromagnetic wave propagates. That material medium, which spreads across the entire space, was called ether. Later in 1887, Michelson and Morley conducted an experiment in which they proved that ether does not exist. Thus, the electric and magnetic fields of the electromagnetic wave oscillating in space with respect to time are self-sustaining. The electromagnetic waves are thus different from other waves, such as sound waves or water waves. Let us discuss them briefly. The first important feature of electromagnetic waves is that they can propagate in vacuum. That is, a medium is not necessary for the propagation of electromagnetic waves. From Maxwell's equations, the velocity of electromagnetic waves in vacuum is written as c is equal to 1 by square root of mu naught epsilon naught. Electromagnetic waves can also propagate in a medium. For example, light is an electromagnetic wave that can propagate in vacuum and in media like glass and water. When the electromagnetic wave propagates in a medium, the electric field and the magnetic field of the wave are described in terms of permittivity epsilon and the magnetic permeability mu of the medium. Hence, the velocity of an electromagnetic wave in a medium is written as V is equal to 1 by square root of mu epsilon. By this expression, we can conclude that the velocity of electromagnetic waves in a medium depends on the electric and magnetic properties of the medium. When light travels from space into a medium, the light gets deviated from the original path. This deviation depends on the refractive index of the medium. Refractive index of a medium is defined as the ratio of velocity of light in vacuum of free space to the velocity of light in the medium. Consider n as the refractive index of a medium, v as the velocity of light in the medium, and c as the velocity of light in vacuum. Then, the refractive index n is equal to c by v. In vacuum, the velocity of electromagnetic waves is a constant. Even for electromagnetic waves of different wavelengths, the velocity is the same. Its value is 3 × 10⁸ meter per second. Since the velocity of light is a constant, it is used to define the standard unit of length, that is meter. 1 meter is defined as the distance travelled by light in vacuum in a time interval of 1 by c seconds, where c is the velocity of light in vacuum. In general, waves carry energy and momentum from one place to another place without the actual motion of the particles of the medium. Similarly, electromagnetic waves also carry energy and momentum. We have learned that the energy density associated with the electric field in free space is written as UE is equal to epsilon naught E square by 2. And the energy density associated with the magnetic field in the free space is written as UB is equal to B square by 2 mu naught. As an electromagnetic wave is a combination of electric and magnetic fields, it carries energy and momentum. This presence of energy and momentum in an electromagnetic wave can be understood by considering some charges in a plane which are perpendicular to the direction of propagation of the electromagnetic wave. The charges are set in motion by the electric and magnetic fields of the electromagnetic wave. Thus, the charges acquire energy and momentum from the electromagnetic waves. Since the electromagnetic wave carries momentum, it exerts pressure called radiation pressure. If U is the energy transferred to a surface by electromagnetic radiation, C is the velocity of the radiation and P is the momentum exerted by the radiation on the surface, then P is equal to U by C. Here, the momentum P is inversely proportional to the velocity of the radiation C. Since the value of C is very high, the momentum exerted by the electromagnetic radiation is negligible. The radiation pressure exerted by the visible light is determined by calculating the momentum using the formula P is equal to U by C. The radiation pressure of visible light is in the order of 7 into 10 power minus 6 Newton per meter square. Different types of electromagnetic waves that carry energy and momentum are useful in various applications, which we will discuss in the other module.
There are different kinds of electromagnetic waves in nature. The arrangement of these electromagnetic waves in accordance with their increasing or decreasing order of frequency or wavelength is called the electromagnetic spectrum. The electromagnetic spectrum broadly contains 7 different kinds of electromagnetic waves. In the increasing order of wavelength, the waves are gamma rays, X-rays, ultraviolet rays, visible light, infrared waves, microwaves, and radio waves. The classification is based on the production or detection of these waves, as otherwise there isn't a sharp distinction between the different kinds of waves. Now, let us briefly discuss the wavelength range, frequency range, production, detection, and uses of all the 7 kinds of electromagnetic waves. First, we shall start with gamma rays, which have the minimum wavelength. In the electromagnetic spectrum, gamma rays have wavelength in the range of 10 power minus 14 meter to 10 power minus 10 meter. Frequency range of gamma rays is from 10 power 23 Hz to 10 power 18 Hz, which lies in the upper frequency range of the electromagnetic spectrum. Gamma rays are produced by the radioactive decay of the nucleus. They are detected by photographic films, Geiger tubes, and ionization chambers. They are used in medicine to kill cancer cells. Now, let us move on to X-rays. Wavelength of X-rays is in the range of 10 power minus 13 meters to 10 power minus 8 meters. The frequency is in the range of 10 power 21 Hz to 10 power 16 Hz. X-rays can be produced by bombarding high-energy electrons with heavy metal targets. They can be detected by photographic films, Geiger tubes, and ionization chambers. X-rays are widely used in different applications such as medicine, spectroscopy, and in industries. Unnecessary or overexposure to X-rays destroys living tissues and organisms. Thus, overexposure to X-rays should be avoided. The next kind of electromagnetic waves in the electromagnetic spectrum is the ultraviolet rays. The wavelength of ultraviolet rays is in the range of 6 into 10 power minus 10 meters to 4 into 10 power minus 7 meters. Their frequency is in the range of 10 power 17 Hz to 10 power 15 Hz. Ultraviolet rays are produced by bodies at very high temperatures, in which the inner shell electrons move from one orbit to another orbit. The Sun is also an important source of ultraviolet rays. They can be detected by photocells and photographic films. Since ultraviolet radiation can be focused into narrow beams with very high precision, it is used in eye surgery. Ultraviolet radiation is also used to kill germs in water purifiers. Exposure to large amounts of ultraviolet radiation causes some harmful effects on humans. It causes skin burn or skin tanning by producing more melanin. But most of the ultraviolet radiations from the Sun are absorbed by the ozone layer in the atmosphere. Thus, the depletion of the ozone layer due to chlorofluorocarbons should be prevented. Now, let us discuss the most familiar form of electromagnetic waves, that is, visible light. Wavelength of visible light is in the range of 4 into 10 power minus 7 meters to 7 into 10 power minus 7 meters. The frequency of visible light is in the range of 7 into 10 power 14 Hz to 4 into 10 power 14 Hz. Visible light emits from an object when electrons in the atoms of the object move from higher energy levels to lower energy levels. Visible light can be detected by the human eye, photographic films, and photocells. The light emitted from or reflected from an object helps us to view the object. The next kind of electromagnetic wave in the electromagnetic spectrum is the infrared wave. Since the infrared radiation heats up objects and surroundings where it is incident, infrared waves are known as heat waves. Wavelength of infrared waves is in the range of 7 into 10 power minus 7 meters to 10 power minus 3 meters. Frequency of infrared waves is in the range of about 10 power 14 Hz to 10 power 11 Hz. Infrared waves are produced by the vibrations of atoms and molecules of hot bodies. These waves can be detected by bolometers, thermopills, and infrared photographic films. Infrared detectors are used in Earth satellites and are also widely used in remote switches and night vision cameras. The visible light absorbed by the Earth's surface is radiated as infrared waves. These infrared rays are tapered by the greenhouse gases such as carbon dioxide, water vapor, ammonium vapor, etc. Thus the gases maintain the average temperature of the Earth. This is referred to as the greenhouse effect. Now, let us discuss the next kind of electromagnetic waves, that is, microwaves. Wavelength of microwaves is in the range of about 10 power minus 3 meters to 10 power minus 1 meter. Frequency of microwaves is in the range of 10 power 12 Hz to 10 power 8 Hz. Microwaves can be produced by klystrons, magnetrons, and gun diodes. These waves can be detected by point contact diodes. These waves are used in radar systems, speed guns, and micro-ovens. Let us also briefly discuss the working of micro-ovens. In micro-ovens, the frequency of microwaves is selected such that it is in resonance with the frequency of the water molecule. When the microwaves are incident on the food material placed in the micro-oven, the water molecules in the material oscillate with maximum amplitude. Thus, the average kinetic energy of the molecules increases, which increases the temperature of the food material. We should not use metallic vessels to place the food material in the micro-oven. This is because if a metallic vessel is used, charge gets accumulated on the metal vessel. This can cause an electric shock, and also the metallic vessel may melt on heating. Finally, we shall discuss about radio waves. Wavelength of radio waves is greater than 0.1 meter. The frequency is in the range of 10 power 9 Hz to 5 into 10 power 5 Hz. Radio waves are produced by accelerated electrons in conducting wires. Radio waves can be detected by receiver aerials. These waves are used in radio, television broadcasting, and communication systems.